Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, my name is Gustin and Lutfiana and I am from Group 10 and here I'm going to present about Cauchy Criterion with my friend Tania. And before that, my ID number is 410-1414101 and for Tania is 410-1419074. In this occasion, we are going to explain about the Cauchy Criterion. For the detail of this material, you can see at the books in the section 3.5. Okay, without further ado, let's go to check the material. The monotone convergence theorem is extraordinarily useful and important, but it has the significant drawback that it applies only to sequences that are monotone. It is important for us to have a condition implying the convergence of a sequence that does not require us to know the value of the limit in advance and is not restricted to monotone sequence. The Cauchy criterion, which will be established in this section, is such a condition. Here the first definition 3.5.1, a sequence x is equal to small xn over real numbers is said to be a Cauchy sequence if for every epsilon greater than 0, there exists a natural number h epsilon such that for all natural numbers n m greater than or equal h epsilon, the terms xn, xm satisfies the absolute value of xn minus xm is less than epsilon. And this is the first example for the part A. The sequence 1 over n is a Cauchy sequence, and we have to prove that the sequence 1 over n is a Cauchy sequence. Here is the proof. If given epsilon greater than 0, choose a natural number h is equal to h epsilon such that h is greater than 2 over epsilon. Then, if n m is greater than or equal h, we have 1 over n is less than or equal 1 over h is less than epsilon over 2. Similarly, for m, 1 over m is less than or equal 1 over h is less than epsilon over 2. Therefore, if nm is greater than or equal h, then the absolute value of 1 over n minus 1 over m is less than or equal 1 over n plus 1 over m is less than epsilon over 2 plus epsilon over 2. So it is equal to epsilon. And since epsilon greater than 0 is arbitrary, then 1 over n is a Cauchy sequence. And for the part B, the sequence 1 plus minus 1 powered by n is not a Cauchy sequence. And here's the proof. To show this, note that the negation of the definition of Cauchy sequence is there exists epsilon 0 greater than 0, such that for every h, there exists at least one n greater than h and at least one m greater than h, such that the absolute value of xn minus xm is greater than or equal to epsilon 0. For the terms xn is equal to 1 plus minus 1n, we observe that if n is even, then xn is equal to 2, and x plus n plus 1 is equal to 0. If we take epsilon 0 is equal to 2, then for any h, we can choose an even number n greater than h and let m is equal to n plus 1 to get the absolute value of xn minus xn plus 1 is equal to the absolute value of 2 minus 0 is equal to 2 is equal to epsilon 0. Thus, the sequence x or small xn is not a Cauchy sequence. And this is a remark. We emphasize that to prove a sequence x is in a Cauchy sequence, we may not assume a relationship between m and n, since the required inequality, the absolute value of xn minus xm less than epsilon, must hold for all nm greater than or equal to h epsilon. But to prove a sequence is not a Cauchy sequence, we may specify a relation between n and m as long as arbitrary large values of n and m can be chosen so that the absolute value of xn minus xm is greater than or equal epsilon 0. And here we have lemma 3.5.3. The lemma said that if the sequence x is a convergent sequence of real numbers, then x is a Cauchy sequence. And here's the proof. If small x is equal to limit of the sequence x, then given epsilon greater than 0, there exists a natural number k epsilon over 2 such that if n greater than or equal k epsilon over 2, then the absolute value of xn minus x is less than epsilon over 2. Thus, if h epsilon is equal to k epsilon over 2, and if nm greater than or equal h epsilon, then we have the absolute value of xn minus xm is equal to the absolute value of xn minus x plus x minus xm, and it is less than or equal the absolute value of xn minus x plus x minus xm, and it is less than epsilon over 2 plus epsilon over 2, and it is equal to epsilon. And since epsilon again greater than 0 is arbitrary, then 1 over n is a Cauchy sequence. And here is lemma 3.5.4. In the previous material, especially in the section 3.2, we have a theorem about a bounded sequence. And here we have a lemma that says that a Cauchy sequence of real numbers is bounded. And the proof is, let the sequence x be a Cauchy sequence and let epsilon is equal to 1. If h is equal to h1 and n is greater than or equal h, then the absolute value of xn minus xh less than 1. By triangle inequality, we have x, the absolute value of xn is less than or equal the absolute value of xh plus 1 for all n greater than or equal h. And if we set n is equal to the supremum of this sequence, the absolute value of x1, the absolute value of x2 until the absolute value of xh plus 1, then it follows that the absolute value of xn less than or equal m for all n element set of natural numbers. And this is the main theorem, the Cauchy convergence criterion 3.5.5. A sequence of real numbers is convergent if and only if it is a Cauchy sequence. And we have to prove this. We have seen in lemma 3.5.3 that a convergent sequence is a Cauchy sequence. Conversely, let the sequence x be a Cauchy sequence, and we will show that x is convergent to some real number. First, we observe from lemma 3.5.4 that the sequence x is bounded. Therefore, by the Bolzano-Weierstrass theorem 3.4.8 that we have studied in the previous meeting, there is a subsequence x prime is equal to small x and k of x that converges to some real numbers x star. We shall complete the proof by showing that the sequence x converges to x star. And since the sequence x is equal to small xn is a Cauchy sequence, given epsilon is greater than 0, so there is a natural number h epsilon over 2 such that nm is greater than or equal h epsilon over 2. Then we have that the absolute value of xn minus xm is greater than epsilon over 2. We give a note that this is the equation 1. And since the subsequence x prime is equal to small x and k of x that converge to x star, there is a natural number k greater than h epsilon over 2 belonging to the set n1, n2, and so on, such that the absolute value of xk minus x star is greater than epsilon over 2. And since k is greater than h epsilon over 2, it follows from the equation 1 with n is equal to k that the absolute value of xn minus xk is greater than epsilon over 2 for n greater than or equal h epsilon over 2. Therefore, if n greater than or equal h epsilon over 2, we have the absolute value of xn minus x star is equal to the absolute value of xn minus xk plus xk minus x star, and it is less than or equal the absolute value of xn minus xk plus the absolute value of xk minus x stars, and it is less than epsilon over 2 plus epsilon over 2, and it is equal to epsilon. And since epsilon is greater than 0 is arbitrary, we infer that limit of the sequence x of limit of the small xn is equal to x stars. Therefore, the sequence x is convergent. And this is the example 3.5.6. For the part A, we have that let x is equal to small xn be defined by x1 is equal to 1, x2 is equal to 2, and xn is equal to 1 over 2 times xn minus 2 plus xn minus 1 for any n greater than 2. It can be shown by induction that 1 is less than or equal xn and xn is less than and equal to 2 for all n element of the natural numbers. And some calculations show that the sequence x is not monotone. However, since the terms are formed by averaging, it is readily seen that the absolute value of xn minus xm is less than or equal the absolute value of xn minus xn plus 1 plus the absolute value of xn plus 1 minus xn plus 2 plus blah 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 until plus the absolute value of xm minus 1 minus xm minus xm, and it is equal to 1 over 2 powered by n minus 1 plus 1 over 2 powered by n plus blah 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 until 1 over 2 powered by m minus 2, and it is equal to 1 over 2 powered by n minus 1 multiplied by 1 plus a half plus blah 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 until 1 over 2 powered by m minus n minus 1, and it is less than 1 over 2 powered by n minus 2. And therefore, if given epsilon greater than 0, if n is chosen so large that 1 over 2 powered by n is less than epsilon over 4, and if m is greater than or equal n, then it follows that the absolute value of xn minus xm is less than epsilon. Therefore, the sequence x is a Cauchy sequence in R. By the Cauchy convergence criterion 3.5.5, we infer that the sequence x converges to a number x. Now, we evaluate the limit of x. Since x is converged to small x, so does the subsequence x prime with odd indices. By induction, we can see that x2n plus 1 is equal to 1 plus a half plus 1 over 2 powered by 3 plus blah 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 until 1 over 2 powered by 2n minus 1. And it is equal to 1 plus 2 over 3 multiplied by 1 minus 1 over 4 powered by n. And it follows that the small x is equal to limit of the sequence x, and it is equal to limit of the subsequence x prime, and it is equal to 1 plus 2 over 3, and we have the final result is 5 over 3. And this is the example B. Let the sequence y is equal to the small yn be the sequence of real numbers given by, this should be y1 and y2. y1 is equal to 1 over 1 factorial, y2 is equal to 1 over 1 factorial minus 1 over 2 factorial, and yn is equal to 1 over 1 factorial minus 1 over 2 factorial plus blah 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 until minus 1 powered by n plus 1 over n factorial. And clearly, y is not a monotone sequence. So if m greater than n, then ym minus yn is equal to minus 1 powered by n plus 2 over n plus 1 factorial plus minus 1 powered by n plus 3 over n plus 2 factorial plus blah 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 until minus 1 powered by m plus 1 over m factorial. And since 2 powered by r minus 1 is less than or equal r factorial, it follows that if m greater than n, then the absolute value of ym minus yn is less than or equal 1 over n plus 1 factorial plus 1 over n plus 2 factorial plus blah 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 until plus 1 over m factorial, and it is less than or equal 1 over 2 powered by n plus 1 over 2 powered by n plus 1 plus blah 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 until plus 1 over 2 powered by m minus 1, and it is less than 1 over 2 powered by n minus 1. It follows that the sequence y is a Cauchy sequence, hence it converges to a limit small y. Then evaluate small y by passing to the limit with respect to m in the above inequality, and we obtain the absolute value of yn minus y is less than or equal 1 over 2 powered by n minus 1. Hence, we can calculate y to any desired accuracy by calculating the terms yn or sufficiently large n, and we obtain the exact value of y is 1 minus 1 over e. And this is the last examples for this part. We have part C, the sequence 1 over 1 plus 1 over 2 until plus 1 over n is diverges. And let h is equal to small hn with the sequence that defined by 1 over 1 plus 1 over 2 until plus 1 over n for n element of the set of natural numbers. And if m is greater than n, then hm minus hn is equal to 1 over n plus 1 plus blah 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 until 1 over m. And since each of these m minus n term exceeds 1 over m, then hm minus hn is greater than m minus n over m, and it is equal to 1 minus n over m. In particular, if m is equal to 2n, we have h2n minus hn is greater than a half, and this shows that h is not a Cauchy sequence. Therefore, h is not a convergent sequence. And for the next part will be explained by my friend Tania.
Okay, thank you, Gustin, for the time. I'm Tania, and I'm going to continue the explanation from group 10. This is about the definition 3.5.7. We say that a square x is equal the small xn of real number is contractive if there exists a constant c, where c is greater than 0 and less than 1, such that the absolute value of xn plus 2 minus xn plus 1 less than or equal c times the absolute value of xn plus 1 minus xn for all n element natural number. The number c is called the constant of the contractive square. This is about the theorem 3.5.x. The theorem 3.5.x said that the every contractive square is a Cauchy square and therefore is convergent. And then the proof, let x be the contractive square. For every n element natural number, we have the absolute value of xn plus 2 minus xn plus 1 less than or equal c times the absolute value of xn plus 1 minus xn less than or equal c power 2 times the absolute value of xn minus 1 less than or equal so on until the c power n times the absolute value of x2 minus x1. Then for m greater than n, we estimate the absolute value of xm minus xn by first applying the triangle inequality and then using the formula for the sum of geometric progression. This gives that the absolute value of xm minus xn less than or equal the absolute value of xm minus 1 plus xm, the absolute value of xm minus 1 minus xm minus 2 plus the absolute so on until the absolute value of xn plus 1 minus xn less than or equal C in bracket C power m minus 2 plus C power m minus 3 plus so on until C power m minus 1 times the absolute value of x2 minus x1. It is equal to C power m minus 1 times in bracket C power m minus n minus 1 plus C power m minus n minus 2 plus so on until plus 1 times the absolute value of x2 minus x1 is equal to C power m minus 1 times 1 minus C power m minus n over 1 minus C times the absolute value of x2 minus x1. It is the less than or equal C power m minus 1 times 1 over 1 minus C times the absolute value of x2 minus x1. Since the C is greater than 0 and is less than 1, and the limit of C power n is equal to 0, therefore the square xn is Cauchy square, and using the 3.5.5 Cauchy convergence criterion, we conclude that the contractive square xn is also convergent. Example 3.5.9. We consider the square of Fibonacci fraction xn is equal to fn over fn plus 1, where f1 is equal to f2 is equal to 1, and fn plus 1 is equal to fn plus fn minus 1. So we have the f3 is equal to f2 plus f1 is equal to 2. f4 is equal to f3 plus f2 is equal to 3. f5 is equal to f4 plus f3 is equal to 5. And f6 is equal to f5 plus f4 is equal to 8 and so on. Also, we have x1 is equal to f1 over f2 is equal to 1. x2 is equal to f2 over f3 is equal a half. x3 is equal to f3 over f4 is equal to 2 over 3. x4 is equal to f4 over f5 is equal to 3 over 5. x5 is equal to f5 over f6 equal to 5 over 8 and so on. We still in example 3.5.9. It showed that the square xn is given inductively by the equation xn plus 1 is equal to 1 over 1 plus xn as follows. Xn plus 1 is equal to fn plus 1 over fn plus 2 is equal to fn plus 1 over fn plus 1 plus fn is equal to 1 over 1 plus fn over fn plus 1. This equal 1 over 1 plus xn. An induction argument establishes xn less greater than or equal a half and less than or equal 1 for all n, so that the adding 1 and taking reciprocal give us the inequality xn greater than or equal a half and less than or equal 1 is equal to 1 plus xn greater than or equal 1 plus a half and less than or equal 1 plus 1 and is equal to 1 plus xn greater than or equal 3 over 2 and less than or equal 2. So we have the 1 over 1 plus xn greater than or equal half and less than or equal 2 over 3. It then follows that the absolute value of xn plus 1 minus xn is equal to the absolute value of 1 over 1 plus xn minus 1 plus 1 over 1 plus xn minus 1 is equal to the absolute value of 1 plus xn minus 1 minus in bracket 1 plus xn over 1 plus xn times 1 plus xn minus 1. It is equal to the absolute value of xn minus 1 minus xn over 1 plus xn times 1 plus xn minus 1. It is equal to the absolute value of xn minus 1 over 1 plus xn times 1 plus xn minus 1. It is equal to xn, the absolute xn of the absolute value of xn minus 1 over 1 plus xn times 1 plus xn minus 1. And then we have the absolute value of xn plus 1 minus xn is equal to the absolute value of xn minus 1 over 1 plus xn times 1 plus xn minus 1 less than or equal to 2 over 3 times 2 over 3 times the absolute value of xn minus 1 is equal to 4 over 9 times the absolute value of xn minus 1. Since we have the absolute value of xn plus 1 minus xn less than or equal 4 over 9 times the absolute value of xn minus 1 for all n element natural number, and c is equal to 4 over 9 where c is greater than 0 and c less than 1. Thus, by definition 3.5.7, the square xn is contractive square. Then, using theorem 3.5.8, we can conclude that the square xn is also convergent. Corollary 3.5.10. If the square x is equal to small xn is contractive square with constancy where c is greater than 0 and less than 1, and if x star is equal be the limit of x, then we have first the absolute value of x star minus xn less than or equal c power n minus 1 over 1 minus c times the absolute value of x2 minus x1. Point 2, the absolute value of x star minus xn less than or equal c over 1 minus c times the absolute value of xn minus 1. And the proof, remember from preceding proof that for m greater than n, then we have the absolute value of xm minus xn less than or equal c power n minus 1 over 1 minus c times the absolute value of x2 minus x1. If we set m be the infinite in this inequality, obtainedly we have the point first, the absolute value of x star minus xn less than or equal c power n minus 1 over 1 minus c times the absolute value of x2 minus x1. And then we will prove the point 2. Remember that for m greater than n, then we have the absolute value of xm minus xn less than or equal the absolute value of xm minus 1 plus the absolute value of xm minus 1 minus xm minus 2 plus so on until the absolute value of xn plus 1 minus xn. Then it is readily established using induction that the absolute value of xn plus k minus xn plus k minus 1 less than or equal c power k times the absolute value of xn minus 1. We infer that the absolute value of xm minus xn less than or equal in bracket c power m minus n plus so on until c power 2 plus c times the absolute value of xn minus 1. It is less than or equal c over 1 minus c times the absolute value of xn minus 1 If we set the p infinite in this inequality, obtainedly we have point 2, where the absolute value of x star minus xn less than or equal c over 1 minus c times the absolute value of xn minus 1. Okay, it is the example 3.5.11. We are told that the cubic equation x power 3 minus 7x minus 2 plus 2 is equal to 0 has a solution between 0 and 1, and we wish to approximate the solution. This can be accomplished by means of an iteration procedure as follows. We first rewrite the equation as x equal to x power 3 plus 2 over 7 and use this to define a square. We assign to an arbitrary value between 0 and 1 and then define xn plus 1 is equal to 1 over 7 times xn power 3 plus 2 for an element natural number. Because x1 greater than 0 and less than 1, it follows that xn greater than 0 and less than 1 for all n element natural number. Moreover, we have the absolute value of xn plus 2 minus xn plus 1 is equal to the absolute value of 1 over 7 times xn plus 1 power 3 plus 2 minus 1 over 7 times xn power 3 plus 2 is equal to 1 over 7 times the absolute value of xn plus 1 power 3 plus, minus xn power 3 is equal to 1 over 7 times the absolute value of xn plus 1 power 2 plus xn plus 1 times xn plus xn power 2 times the absolute value of xn plus 1 minus xn less than or equal 3 power 3 over 7 times the absolute value of xn plus 1 minus xn. Therefore, xn is contractive square and hence their axes are such that limit xn is equal to r. If we pass to the limit on both sides of the quality xn plus 1 is equal to 1 over 7 times xn power 3 plus 2, we obtain r is equal to 1 over 7 times r power 3 plus 2, and hence r power 3 minus 7r plus 2 is equal to 0. Thus, r is a solution of the equation. We can approximate r by choosing x1 and calculating x2, x3, and so on successively. For example, if we take x1 is equal to 0.5, we obtain the value of x2, x3, x4, x5, x6, and so on. You can see the value of x2, x3, x4, x5, and x6 in this slide. To estimate the accuracy, we note that the absolute value of x2 minus x1 less than 0.2. Thus, after n step, it follows from corollary 3.5.10 number 1 that we are sure that the absolute value of x star minus xn less than or equal 3 power n minus 1 over 7 power n minus 2 times 20. Thus, when n is equal to 6, we are sure that the absolute value of x star minus x6 less than or equal 3 power 5 over 7 power 4 times 20 is equal to 243 over 48,020 less than 0.0051. Actually, the approximation is substantially better than this. In fact, since the absolute value of x6 minus x5 less than 0.000005, it's follow from corollary 3.5.10 number 2 that the absolute value of x star minus x6 less than or equal 3 over 4 times the absolute value of x6 minus 5 less than 0.00000004. Hence, the first 5 decimal places of x6 are correct. Okay, this is the end of our presentation. I'm sorry if we have some mistake. Thank you. Wassalamualaikum warahmatullahi wabarakatuh.